Hi everyone, today you're going to be starting chapter 10. It's on sequences and series. This first lesson is just an introduction, and in the next lessons we'll get into more specifics. Alright, so what is a sequence? A sequence is just an ordered list of numbers. That's all it is, it's a list. And each number in a sequence is called a term. Right? Just like in a matrix, we had entries or elements. The numbers in a sequence are called terms. All right. A finite sequence is a sequence that contains a finite number of terms. So you know exactly how many terms are in there. 5 terms, 50 terms, 100 terms, and so on. So for example, 1, 3, 5, 7, 9, this is a finite sequence. It's got 5 numbers in there. An infinite sequence contains an infinite number of terms, meaning it just keeps going and going. So like, for example, 2, 4, 6, 8. This looks like this is all of the even numbers up to infinity. Okay, so it keeps going. All right, let's talk a little bit about notation. The way we label terms in a sequence is by giving them subscripts. So if you have a sequence, then each term would be A1, A2, A3, A4, okay? Or you may start numbering them at A0. This is sometimes a matter of preference. Sometimes the problem just lends itself to it. You'll see as we do more and more problems. So if you start labeling them like that, then your terms are A0, A1, A2, A3, and so on. A generic term is given the label AN. All right, so if you just talk about, some random term in the sequence, okay, that's just AN. And what about terms that come before or after AN then? Okay, if they come before or after AN, then they'll be labeled as AN-1 or AN+1. Okay, so what does that mean? Suppose the 5th term is AN, right? Then the 4th term would be AN-1, right? Because if n was 5 here, then it's n-1 here, so that's AN-1. All right. Well, what about the 6th term? The 6th term would be called AN+1. Okay. So, for example, if you have a list, then you would call the middle one, you would call this AN. And then the ones that come before it are AN-1, AN-2, and then it's N+1, N+2, and so on and so forth. Okay. Sometimes a sequence can be represented as a function. And in that case, AN is the nth term. And sometimes you have a formula which explicitly defines how to find each and every single term, right? That's called an explicit formula to find the nth term. So for example, this in example 1 is an example of an explicit formula. So it's telling you AN is 3n+1 over 2. And it's telling you to find A4. All right. So notice here you have the subscript n, and that same n appears in your formula, right? So suppose you're looking for A4, then n is 4, and all you have to do is plug 4 in there and you find A4. So let's just do that. A4 is equal to 3, 4, plus 1 over 2. So this is equal to 13 over 2. All right. So what this says is that the 4th term in the sequence is 13 over 2. Now, how would you find, let's say, the 57th term? A57 Well, you would just plug 57 into the formula for n. Okay? All right. A lot of times sequences have a pattern, and if you want to find consecutive terms in the sequence, what you first have to do is you have to find their pattern. All right, so here it says find the next 4 terms in the sequences. Well, let's first find the pattern. All right, and sometimes people just look at a sequence and they just see the pattern. I'm not one of those people. I have to do a little bit of an investigation, so let's just do that. All right, what I like to do is this. Okay, so to go from one term to the next, right, is there a pattern? So what does it look like it's happening here? How do you go from 3 to -1? Well, you could either add, subtract, multiply, and divide, square, all those sorts of stuff. Well, it looks like we're subtracting 4 here. Well, does that hold for this one? Yeah. Does that hold for this one? Yeah. So it looks like it's safe to say that the next terms are just going to be subtracted by 4. So the next 4 terms will be -13, -17, -21, -25. Okay? Now, what's happening here? Well, how do you go from 2 to 5? Well, it looks like you add 3. How do you go from 5 to 10? It looks like you add 5. Here, you add 7. Oh, look, at each step, you're adding the next odd number. So next, I'm going to have to add 9, and then whatever I get, I have to add 11, and whatever I get, I have to add 13, and I have to add 17. So 17 plus 9, that would give me 26, and then the next step would give me 37, 50, 67. So those are the next numbers in the pattern. All right. So here you're given the explicit formula, and if it says to find the next 4 terms, so basically we're going to start from A1. Again, whether it's A1 or A0, it'll be specified. If it's not specified, you could just pick one. Let's start with A1. This will be, since n is 1, you put 1 in here. 1 cubed plus 1 is 2. A2, 2 cubed plus 1 is 9. A3, 3 cubed plus 1. And if we follow the same thing, then it's 4 cubed plus 1, and it looks like that would be 65. Okay? All right, so this is when you can define the sequences using an explicit formula. Sometimes we define sequences using a recursive formula. What recursive sequences are basically is they have a couple of initial values, 1, 2, 3, and then each of the next terms are found based on doing something to the previous term. So for example, if you want to find A5, then you have to do something to A4 and maybe A4 and A3, and that's how you find A5. If you want to find A6, you have to use A5, and so on and so forth. Okay? So an example is this. So it tells you, okay, the first term in this sequence is 1. A1 is 1. And then every other term is an minus 1 plus 2. Now, if I see an minus 1, I immediately think, oh, the previous term. So, if I'm looking for the 5th term, I have to take the 4th term and add 2 to it. Okay? So that's how that works. Let's do an example here. It says find the 4th term of the recursively defined function. All right? So A1 here is 3. Okay. Well, what would A2 equal to then? Well, let's see. A2, all right, so what is AN? It's 3 times the previous element, AN minus 1, so 3 times 3 minus N plus 2. Okay, so A2 would be 9 minus 2 plus 2, that's just 9. All right, now let's see what A3 is. A3 is 3 times the previous number, which was 9, minus n plus 2. So 27 minus 1 is 26. And now for A4, that's the big one, that's the one we're looking for. It's 3 times the previous element, 26, minus n plus 2. So this is going to be 76. All right. Now, what about the Fibonacci sequence? You hear it all over the place. So the Fibonacci sequence basically is responsible for the golden ratio, and you see it in all sorts in nature. We're gonna do a lot more with it. For now, let's just try to generate some numbers. So the way the Fibonacci sequence is defined is A1 is 0, A2 is 1, and then every other one is found by an minus 1, so that's the previous one, plus an minus 2. So basically, what do? If you want to find element number 5, then you have to take the number that came right before it plus the one that came right before that and add them to each other. So basically, each element is the sum of the previous two that come before it. Okay? So it says find the fourth term. All right. Well, A1 is 0. A2 is 1. Now, A3 is the previous two numbers added to each other. And A4 is the previous two numbers added to each other. So 1 plus 1 is equal to 2. Okay? So if you write the Fibonacci sequence then, how does it look? It's 0, 1, and then we said the third one is 1. And then for each one, you have to add the previous two. So 1 plus 1 is 2, and then you add the previous two, you get 3. You add the previous two, you get 5. You add the previous two, you get 8, and you could do that all day. Okay? Next time you guys are at the beach, that's what you could do in the sand. Okay. So let's talk about convergent and divergent sequences. Basically what this is, to think about this, it's easy if you think about end behavior, right? So we basically have two different types of functions, right? Take a look at this function. And if you wanted to see the end behavior of this, and if this was f of x, and if we said, what is the limit of f of x as x approaches infinity? Well, as x approaches infinity, where does the graph go? It goes up to positive infinity, equals positive infinity. Now, what if you had a function that looked like this? Okay, well, what is the limit of, let's call this g of x? What is the limit of g of x as x approaches infinity? Well, look, it looks like g of x is approaching 0 as x approaches infinity, right? So the end behavior here is 0, right? So do you see the cases here? One is approaching, this one, g of x is approaching a finite number. And in the other case, it goes to infinity, all right? In a similar fashion, sequences may also approach a specific value or a limit. And if the terms of a sequence approach a unique number, we say the sequence has a limit and it converges. Otherwise, if the terms in the sequence do not look like they are approaching a specific value, then we say that it diverges. So let's take a look at these two examples here. What this is a plot of the successive terms of a sequence. So this is A1, A2, A3, A4. So look, A1 is 1, A2 is 0.4, then 0.2, then 0.1, and so on and so forth. And little by little, look, this is, for example, AN, right? What value is AN approaching? It looks like the terms are approaching 0, right? Little by little, they're going to get very, very close to 0. Since the terms in this sequence are approaching a specific value, we say this has a limit and it converges. Well, look at this one. A1, A2, A3, A4. Well, it looks like there is some sort of a pattern, or maybe not. Do I know by the time I reach AN, like the millionth n, what value these terms are going to be approaching? No, I have no idea. So I say this is a series, a sequence that that diverges. All right. So let's take a look at this one and let's see if these will converge or if they will diverge. What we're going to do is we're going to generate each of these terms here. So what I'm going to do is I'm going to find A1. And how do I do that? That's negative 4,000 times negative 1 over 4 to the power of 1. And then A2 is going to be negative 4,000, negative 1 over 4 to the power of 2. Okay? So the first number is going to be 1,000. Then we're going to get negative 250. Then A3, we're going to get 62.5. A4, we're going to get negative 15. A5, 3.9. A6, negative 0.97. All right? Okay, so what's important here? You have a negative number right here, and it's raised to an exponent, right? So if that exponent n is an odd number, then this value is going to be a negative. Times this negative, the whole value will be positive. But if the exponent is even, 2, 4, 6, 8, then this will be positive times a negative, you get negative. So if you look here, for odd values of n, you get positive values. For even values, you get negative values. Okay, now this is important because if later you want to define a sequence that alternates in sign, plus minus, plus minus, plus minus, this is one way to do it. You have a negative number raised to the power of n. Usually we say like negative 1 to the power of n. Keep that in the back of your mind. We're going to get to that at some point in this chapter. Okay, let's just quickly plot these. So the first number is 1,000. So when n is 1, it's 1,000. And then it's negative 250. And then it's 62.5. And it's negative 15. And it's 3.9. See that, by the way, we don't connect these. This is not a line plot. They're just distinct points. But you can see that as n increases, right, the value of the terms is approaching 0. So this series is going to converge. Okay? All right, let's take a look at this one. If we do generate the values here, now let's just take a look. Again, you have a negative number here raised to an exponent, so you can already guess now that these terms are going to alternate in sign, right? So A1, and we do it the same way as we did before. Okay, A2 is 2, negative 4, 8, A5 is negative 16, A6 is 32, A7 is negative 64, A8 is 128. You can tell I totally got carried away here, so I was having a little too much fun, I think. All right, let's plot these. A1 is negative 1, A2 is 2, A3 is -4. A4 is 8. I'm not looking for NASA precision here, obviously, right? We're just going to eyeball these values. I skipped one. Okay, I'm looking for a little bit more precision than that. A5 is -16. A6 is 32. 20, 32. A7 is -64. A8 is 128, all the way up there. So you can see that this is clearly diverging, right? Because as n increases, I have no idea where this is going to end up, and they're not approaching a specific value. So this is one that diverges. All right, so how many of these points do you need? 4 or 5 at least, enough to definitely be able to make a decisive guess. Okay. Let's take a look at this one. So same situation. This time we don't have a negative to the power of an exponent, right? So we can't say that the terms are going to alternate. A1 is 0.1. A2 is 0.0067. A3 is 0.00006. A4 is 0.40 and 57. Right? So what do you think? Converge or diverge? I think clearly this is going to converge, right? So we start at 0.1 and then each one is going to be less and less and less. Okay? So this is going to converge because it looks like as n is increasing, the values are going down to 0. All right, that much about sequences. What is a series? Well, a series is this. If you took a sequence, which is just separate distinct numbers, and if you added up all the numbers in that sequence, that becomes a series. So basically, if I replace the commas in a sequence with addition signs, I make it into a series. Okay? A series is the indicated sum of all the terms of a sequence. A finite series is the indicated sum of the terms in a finite sequence. And an infinite series is the indicated sum of all the terms in an infinite sequence. So that's kind of cool, right? Because, okay, a finite series, fine. There are 100 numbers, I add them. There are 200 numbers, I add them, and then I'm good. An infinite series is, I have a series that has an infinite number of terms in there. They never ever end. And now I want to find the sum of those numbers, and so I know you're going to say, well, wait, that's just infinity, because if you keep adding infinite numbers, you're just going to get infinity. Well, that's the cool part, is not necessarily, okay? All right, so again, a little bit of notation. Suppose you have a series of 100 terms. If you just want to find the sum of the first 20, right? So the sum of the first n terms, oh, that should be of a series, is called the nth partial sum, denoted by Sn. So for example, if I just wanted to find the sum of the first 20 numbers, that would be S20. To find the nth partial sum, surprise, surprise, you have to find all the terms up to an, and then you have to find the sum of those terms. Okay? So let's find the fifth partial sum of this guy. Well, now we know how to get these numbers, right? A1 is 1 squared minus 3, which is -2. And then A2 is 1. A3 is 6. A4 is 13. A5 is 22. And now, if I want the fifth partial sum, that's S5, and I'm just going to add those numbers, nothing mysterious. Turns out, that's a cute little 40. Okay? This is the same situation here. So A1 is 3, and I only want S4 here. A3 is 3 over 4. A4 is 3 over 8. All right, what do you notice about this? You have 6 over 2 to the n. The numerator is a constant. The denominator is something that is being raised to the power of n. For each successive term, n is increasing. A1, A2, A3, A4. So for each term, this denominator will get bigger. Right? The denominator gets bigger. As the denominator gets bigger, the entire fraction will get smaller. So if I want to find S4, right, I start with 3. And then the next term is smaller. It's 1.5. The next one is smaller still and even smaller. So as you know, if we had to continue this, you could see that the numbers are going to get smaller and smaller and smaller. So what do you think? Would that converge or diverge? I know you know. Okay, so S4 would be 45 over 8, which is 5.625. I'm giving you fraction and decimal for diversity here. All right? Okay. And now, everybody's favorite, sigma notation. What is sigma? Sigma is the Greek letter that makes the S sound, like S. This is lowercase sigma, and this is uppercase sigma. All right, so if you're ever on Jeopardy and that comes up, now you know, and you give me on-air credit, okay? All right. This is basically, sigma is used for sum, and it's basically a shorthand way to tell us how to sum things. So for any sequence, the sum of the first k terms is denoted by sigma, and this tells you n equals 1 to k. Basically, this is telling you add all of the terms from A1 to AK, okay, of the series AN. Let's take a look at this one, and look, you'll see an example here. So I have a series, and this is the explicit formula to find each of the terms, right? So usually we were writing this as AN equals n squared minus n. So now this notation is telling me, this is code, it's telling me, all right, this is how you're going to generate your numbers. Now add up all the terms from A1 to A4, okay? So how are we going to do this? Well, let's see. A1 is 1 minus 1, which is 0. A2 is 6. A2 is 2. A3 is 6. A4 is 12. And that's all I need, right? Is I need A1 to A4. So this, I just add 0 plus 2 plus 6 plus 12, and I get 20. Okay? I just want to comment a little bit on the parentheses here. Make sure you do put parentheses because so suppose you have this minus n. You don't want to leave things as being ambiguous. So if you don't put parentheses, it could be taken as, okay, sum up all of these, and then once you get the sum, subtract an n from it, right? If you want it to be the sum of n squared minus n, you want to go in there and you want to put parentheses around it, okay? Just a little bit of notation. Okay, now take a look at this. This is telling you, all right, you've got your terms. You can generate your terms like this, 3 times 1 over 10 to the n. And now it says, add up all the terms from n equals 1 to infinity. So all of them to infinity. Okay, so this is one of the ones. Well, okay, we're adding infinite terms. It's obviously going to be infinity. Well, is it though? let's see. What do we have here in the denominator? What we have is what we saw earlier. We have in the denominator a constant to the power of n. That means as n gets bigger, the denominator will get bigger, making the entire fraction smaller and smaller and smaller and smaller and smaller. Okay? Some people take a look at this and they just see it. I was never one of those people. I would have to write things down. So let's write things down. Let's just generate a couple of numbers and see what we're going to get here. All right, A1 is going to be 3 times 1 over 10. Okay, that's just 3 over 10. A2 is 3 times 1 over 100, right? Well, A3 then is going to be 3 over 1,000. And what's A4? 3 over 10,000. Okay, what's happening here? Well, let's see. Let's just write this up. So the sum from n equals 1 to infinity of this cute little mess is equal to 3 over 10, 3 over 100, 3 over 1,000, 3 over 10,000 plus ... right? Okay, what's 3 over 10? Well, I think that's 0.3, and this is 0.03, and this is 0.003, and this is 0.0003, right? Okay, so what is this then? It looks like this is 0.3 with a bar, right? Okay, so I've written this once. I will, I'm not a fan of a number with a bar over it. But what is this? What is this in fraction form? What is the exact form of this? It's 1/3. Okay? Okay, tell me this is not cool, right? That if you see this, right, and that just ends up the sum of the infinite number of terms gives you 1 over 3, right? And this is how you do it. Run through it. You're going to be doing a couple of them in your homework. Run through it. Write it out. Ration it out. Rationalize it. At some point, you'll just begin to see it, or maybe you'll have to write it out each time. Either way is completely fine with me, but it doesn't take away from how cool that is. Okay? All right. Now, this is my favorite. I can't say everybody agrees with me, but all right, let's just do this. It says to write the series in sigma notation. So basically, I want to come up with a notation like this, whereby if I generate these numbers, A1, A2, A3, A4, this is what I'm going to get. Okay, how do we do that? Well, what we're going to do here is this. So it says n equals 1. That's the lower bound, right? That's what that is. That's the lower bound. So that means when you do your sigma, it's going to be n equals 1 to some number. Okay? Okay. Since the first n is 1, that means here this is n equals 1, right? So the first one is A1, where n equals 1. And then this is n equals 2, n equals 3, 4, 5, 6, 7, 8. To do this, what you want to do is you want to find a pattern, a connection, some way that the value of n is connected to the term, to the value of the term. And that operation has to be the same for this n and that term, for this n and that term. Okay, so for example, how do you go from 1 to -2? What would you do to 1 to get -2? Well, one thing is you could multiply it by -2. Okay, so times -2. Is that the same here? Can I do 2 times -2 and get -1? No. Can I do 3 times -2 and get... No. So obviously, multiplying by -2 is not the answer. I have to come up with something else. And sometimes simpler. Sometimes they're a little bit more complicated. Sometimes you have to take the 1 here, you have to square it and subtract something, or you have to square it and divide by something, all right? Well, let's focus on this one now. What do I do to 1 to get -2? So we think, and I go, oh, what if I subtracted 3? Okay, let's see, 1 minus 3, yeah, that's -2. Okay, what if I do 2 minus 3? Do I get -1? Oh my God, I do. What if I do 3 minus 3? Do I get 0? I totally do. 4 minus 3, yup. 5 minus 3, yup. So what am I doing? Whatever my value of n is, I'm subtracting 3 from that and getting my terms. Okay, so that must be the formula, right? So in here I say, okay, it's n minus 3, all right? And I'm almost done. So I started with n equals 1, and what's my final value of n? I go up to n equals 8. There we go. Okay, so that's the answer. Alrighty. Thank you for listening, everybody. This is the homework. It's going to be due the day after your test. Okay? So check on Haiku for when this one is due. Thank you very much, and I'll see you guys in class.